So it's a great pleasure to welcome Mark Hughes, he's visiting from Brigham University. We're not very good with formal introductions, so I will skip them and let people find out more about you by Googling you or their own favorite search engine. He's going to tell us about machine learning approaches to low-dimensional topology.
All right.
For being cooperative to give similar charts.
Oh no, it's my pleasure. I'm very happy to be here. Thank you for the invitation to speak to you. For background, I am a low-dimensional topologist. I'm not a physicist. I do talk to a lot of physicists and have sort of working collaborations with physicists, but I recognize that this is probably largely a physics group, and so I'll try and talk about things. My talk is fairly flexible. I've got slides, but I've got little jump points that I can jump from place to place. So if we want to delve into some topic a little bit deeper, or feel free to ask as many questions as you want. I also tried to pick topics that are sort of relevant to physics, I guess I should say, so this idea of using machine learning in mathematics, I feel like applications of machine learning are sort of a lot more advanced and sort of more well adopted in physics. So that's partially why I work with a lot of physicists, because they've adopted a lot more of these ML techniques in some areas of physics. And in mathematics, we're sort of I'd say we're a little bit slower, in adopting some of these techniques. And so I, as a low-dimensional topologist, wanted to just kind of explain some of the uses, some of the places you might try and use ML and AI to sort of answer questions in low-dimensional topology, and why I think some of these questions might be interesting. So let's see, meeting is being recorded. Okay, let's see, is this going to click? No, it's just going to beep at me. Let's see. There we go. Okay, maybe this will work. Okay, so obviously, in the past 2 to 3 years, I mean, really since ChatGPT came out, there's been just headline after headline about sort of what AI can do, sort of the generative capabilities and some of the shortfalls of AI. And so probably like a lot of you, I was initially curious when ChatGPT came out, what can it say, what can it do for mathematics, how can it make my job easier? And so I was teaching linear algebra at the time, and I asked it to just create a college level linear algebra exam using about eigenvectors and eigenvalues in LaTeX, so I don't have to, create exams for my class. I thought this was going to simplify my life. And it creates something that looks like, it's maybe a little hard to see on the screen, but if you sort of zoom in a little bit, it looks like a reasonable exam. But if you, there is some LaTeX formatting issues. For example, I think this is supposed to be a 2x2 matrix. It didn't, put the correct formatting in. But if you, oh, awesome. Let's see. Yeah. So if you kind of zoom in and look at one of the questions it's asking you to is essentially show that the characteristic polynomial of a given matrix has infinitely many roots, which is not obviously true, right? Like that 2x2 matrix has at most 2 eigenvalues, so certainly this sentence here cannot be true for all lambda. So it sort of is good at, at least sort of current state of AI is that at least some of these off-the-shelf techniques are good at producing things that look convincing, but maybe lack some of the underlying internal logic, okay? So what am I interested in? Well, I'm primarily interested in knot theory, and low-dimensional topology, a knot is just, let's see. I'm not sure which view is better. Oh, there, that's pretty good. Yeah, there we go. That's pretty good. A knot is just the image of an embedding of a circle into three-dimensional space. You can consider knots inside of more complicated three-dimensional manifolds, but for a perfectly good place to start with your foray into knot theory is just knots inside of R3 or inside of the three-sphere S3. I know knots show up a lot in physics, and so that's sort of where a lot of the interaction with me and some of my, the people that I talk to in physics are. But I also recognize that maybe not everyone in theoretical physics thinks about knots, so feel free to tell me, if you have questions or if I'm going too slow, I'm happy to adjust speed here. But really, so when we study knots, typically what we do is we consider knots up to isotopy. So we think of these things as living in some three-dimensional space, and we want to allow them to sort of bend around and move and and sort of deform, but without passing through each other. We don't want sort of strands of the knot to pass through themselves. Typically, we represent knots using what are called knot diagrams, which are just two-dimensional projections. And we have a nice calculus of knot diagrams that basically says, two diagrams, if I take isotopic knots and I project them down, then if the original knots are isotopic, then the diagram should be related through Brigham-Meister moves, a sequence of Brigham-Meister moves and planar isotopies. And so this allows us to sort of take three-dimensional knot theory and convert it into sort of a two-dimensional diagrammatic calculus, which ends up being pretty useful and a pretty good way to do it. Okay. So any questions or comments? Okay. So knot theory shows up in a lot of fields. Biology, there are people who sort of study knottings of DNA and protein. In physics, quantum field theory and string theory, and that's all that I'm going to say, because I don't know enough to say anything more than that, especially in probably this group here. In low-dimensional topology, the reason that I care about knots is because it allows us, we have, for closed three-dimensional manifolds and four-dimensional manifolds, we need some hands-on way of describing the topology of these spaces. And it turns out that you can describe the topology of a smooth four-manifold or a three-manifold using just knot diagrams with some decoration. So for example, I can represent the Poincare homology sphere, which is a which is a non-simply connected closed three-manifold that has the same homology as the three-sphere. And I do that by sort of drawing a knot diagram and fixing a framing to it. And essentially what this means is I'm going to take the three-dimensional sphere, I think of my knot as living inside of it, and I'm going to drill out a little neighborhood of this knot, and I'm going to sort of take that solid torus out of my three-dimensional sphere, and then I'm going to glue it back in, but with a certain twisting of the boundary, and that gives me a new closed three-dimensional manifold, which happens to have trivial homology. There are sort of similar constructions one dimension higher, and I can sort of use, this is a link diagram, so it's a two-legged knot but with multiple components, and by sort of drawing a picture like this, I can sort of convey all the information you would need to construct the E8 manifold, which is a manifold that has the four-dimensional manifold with no smooth structure. And really any closed, well, I should be a little bit careful here because this can't be closed off smoothly, but it can be closed off topologically, and so but essentially, knots and knot diagrams give us sort of the building blocks to construct three- and four-dimensional spaces, and they give you a nice...
What did you mean by the E8 manifold as a four-dimensional manifold? It has the E8 holonomy, is that? Or
the intersection form is the E8 form. So I'm not sure if you're familiar with intersection forms on four manifolds, but essentially you look at the two-dimensional homology of the four manifolds. So these are homology classes that are represented by closed surfaces, and you can look at sort of the essential intersections of given two homology classes, two-dimensional homology classes. You can look at their intersections and sort of count the number of points with sign. That gives you an intersection form on the second homology, and that's sort of the E8 homology, or that's the E8 form.
Okay, and that's why it looks like the Deacon diagram.
Yeah.
What are +1 and -2?
So so this is a procedure called Dane surgery. So I'm drilling out a solid torus around the knot, and then I'm gluing it. If I take the solid torus in one hand, and I can draw pictures too, and I take the complement of the solid torus in the other hand, they both have their boundary are both a torus, a two-dimensional torus. There are lots of self-diffeomorphisms of the torus, which means that there's basically lots of ways you can take this solid torus and glue it back into the complement non-trivially.
So what's the +1?
The +1 tells me that as I'm gluing it back in, I'm going to give it a twist. I'm going to give it one full twist.
Some boundary on the.
I suppose the question is, the one full twist around what cycle?
Oh, so around, so so there's some convention here where you pick a longitude and a meridian, so you'll take like the, what I would do is I would take a zero-framed meridian, longitude, zero-frame longitude. So what I would do is I'd sort of take, if I imagine sort of two parallel curves like this, and this isn't zero-framed, the full twist that I'm going to give it is in this direction as I'm going around. So when I'm gluing my solid torus and I'm gluing it with a full solid twist.
Framed torus?
Yes.
Framed not.
Yeah, so it has a canonical framing if it's in S3, just to take the zero framing. So you take a parallel thing that's, there's a way to specify a zero framing, and the +1 just says you twist it with respect to that framing.
What about another one? What is -2? So
this is sort of the same thing. In this example here, or in the E8 manifold, the camera's off, we can't see. I guess is that your camera that should be on?
Should be.
Okay. Maybe you mean this.
Oh yes, sorry, the blackboard camera is probably on. Yeah.
So in this picture here, we're thinking of everything as taking place inside the 3-sphere, but this 3-sphere is the boundary of a 4-dimensional ball. And so what I'm doing, what each of these circles is telling me, is it's telling me to take a copy of D2 cross D2. Now, in the boundary of D2 cross D2, there's a copy of S1 cross D2, so I sort of think of this as being like, I can't draw 4-dimensional things very well, but I think of sort of one of these D2 factors as being like this horizontal disk. The other D2 factor is like a disk in this direction. And if I look at sort of, there's a copy of S1 cross D2 in the boundary. So I get this solid torus that lives in the boundary. And what this is telling me to do is I'm going to take this copy of D2 cross D2, and I'm going to glue it along here, but now I'm adding -2 twists as I'm doing that gluing. So it still specifies a framing, but now I'm sort of gluing on a copy of D2 cross D2 instead of doing this surgery operation over here.
But Dane surgery gives all three manifolds.
Yes, yeah.
How about that?
So, well, maybe let me make a quick connection between the two, and then I'll try and answer your question. So, it turns out that if you take the boundary of this thing here, the boundary of this thing is just Dane surgery, is what you would get by doing Dane surgery along the same diagram. So really, like, Dane surgery is just happening along the boundary. This is sort of a 4-dimensional thing that is sort of gives you Dane surgery on the boundary. It's known that every smooth 4-dimensional manifold has a handle decomposition, and from a handle decomposition, you can come up with a diagram like this. It's called a curvy or a handle body diagram. So for smooth 4 manifolds, it captures everything.
So is this giving a manifold or just a topological space?
So this will give you a manifold, a smooth manifold in particular, yes. Now I'm sweeping a little bit under the rug, because technically what happens here is you start off with a ball, you attach these pieces here, and then what you want to do is you want to cap it off with what are called 3 handles and 4 handles. Now this diagram here cannot be capped off smoothly with 3 handles and 4 handles. So that's why it has some interesting topological issues going on. But in general, if you can cap it off with 3 and 4 handles, it can be done uniquely, and so therefore the smooth topology of that 4 manifold is uniquely characterized by this diagram. And every smooth manifold has such a diagram.
Is that what is called handle body decomposition?
Yes, yeah.
And does it really make a difference that they're all -2s? Could I switch everything to be +2s, or is there an actual difference?
You would, it would just change everything up to orientation.
It's the opposite orientation.
Yeah.
And the same as with the two.
Yeah. So the sign of the framing just is an orientation. Yeah. So for example, the curvy diagram or the handle body diagram of CP2 is just this, and CP2 bar is that. Yeah. Any other questions or comments? No? Okay. So the knots sort of are a nice, I mean, even knot theory sort of started in the 1800s, and actually at the time I think it was sort of proposed that atoms, the sort of atomic decomposition, atoms were composed of like sort of swirling vortices in the ether, and so these were like little knots that were sort of swirling vortices in the ether, and different knot types gave you different atoms in the periodic table. From what I understand, you could correct me, that's no longer accepted. I don't know. I've been told that's no longer accepted. I don't know much beyond that, but it sort of kicked off this idea. This idea that sort of the chemical or atomic, like classifying elements, came down to classifying knot types. Sort of kicked off this sort of hobby. Maybe I don't know. Maybe hobbyist, but sort of this sort of process of like trying to tabulate all different knot types. Okay, so even in the 1800s, people were sort of tabulating different knot types and putting them into tables. And nowadays, because knots sort of now form an infinite data set, they sort of are ripe for sort of, at least naively speaking, for sort of trying to apply techniques of machine learning or big data, right? It's a big data set, so why not try to apply techniques of big data? And to try and answer questions and find patterns and things like this. So, nowadays, sort of, there are a few sort of key online tables of knots. One that is really handy is this knot info, where they've essentially, tabulated all knots up to 13 crossings, or that have diagrams up to 13 crossings. And you can't really read it here, but there are lots of invariants here. So, for example, if you want to look at all 13 crossing knots, and you want to know what the Jones polynomial of those knots are, you can kind of click and see at a glance what those are and download them. So we've sort of continued this process of building larger and larger knot tables, and along with it, we're now computing invariants to go along with them. So when I say machine learning and I talk about trying to apply techniques of machine learning, what do I mean? Well, I sort of see, at least in relation to topology, sort of three branches or ways of sort of trying to apply machine learning to knot theory. The first is through what's called supervised learning, and this is just essentially training things like neural networks to make predictions about knots that you have in a data set. So say you have some knots and you want to try and understand what if there's a relationship between the Jones polynomial and the slice genus. Maybe you can train a neural network to try and take as input the Jones polynomial and spit out, say, the slice genus's output. How well can neural networks do things like that? There's reinforcement learning, which I think of as sort of, you've got some problem that you want to solve, and you've got some large search space that you want to search through to look for an optimal solution, but there's no real a priori good way to search through this search space to try and find your solution. Well, can you train a neural network or some sort of more complicated agent to try to find an optimal search strategy through that space? And the last one is sort of, I think of as generative learning, which is where it's just like kind of ChatGPT or DALL-E or Midjourney, where you type in some prompt, some instructions, and you try and have it produce something that sort of satisfies the properties you're looking for. So I will kind of focus on the first two here. I think there's sort of really interesting approaches to trying to use all three of these, and they're definitely not as you can try and do generative learning using reinforcement learning, or you can they're all sort of related in lots of ways. But I'm going to sort of focus on the first two here. But I'm not going to leave generative learning alone, because we have nice image generation software. So, for example, I did this a couple of years ago, where I was like, what does DALL-E, this was DALL-E 2 at the time, what does DALL-E 2 know about knot theory? So I asked it to produce a hyperbolic knot with cipher genus 2 and trivial Alexander polynomial, and this is what it gave me. I don't recognize any of these knots. I don't actually know that any of them are knots. They kind of look like they just crash through each other, and they're colored. I think they're colored interesting ways to sort of confuse the human eyeball and make me think it's a knot, but if you look closely enough, these are just kind of garbage. But AI has advanced a lot in the last couple of years, so I wanted to give it a reasonable chance. So like a couple of months ago, I asked it to produce a hyperbolic knot with cipher genus 2, and it created these beautiful looking pieces of artwork. Again, neither of these are knots that I recognize. They're really not even like well-defined knots. I think if you look closely enough, things are not connected in the right way. And it's like when you generate like images, you say generate an image of this, and then it looks like a good image, but then you look closely and someone, you know, in the photo, like a person's got an arm around and there's an extra hand coming through. Like it's just like something fishy's going on here.
Can you explain what is meant by hyperbolic knot and cipher knot?
Yes, so I'll talk about cipher genus. Hyperbolic knot is a knot who, if you look at the complement of the knot, it admits a complete hyperbolic metric, or a metric with constant curvature -1.
Okay.
So
cipher manifolds I have heard, but cipher not.
a cipher genus?
Yeah.
I'll show you some pictures. I've got some pictures of cipher genus in a second. So
Can I ask another question? Long ago, I saw that if you have an arbitrary knot on, say, R3 or
Yeah.
any manifold, take out a knot, then look at pi 1 of the complement.
Yeah.
It completely classifies the knot.
Yes, it completely classifies prime knots, or so it's not quite enough to look at the isotopic class of pi 1. But if you look at it's not quite enough to look at the isomorphism type of the group pi 1. But if you specify the group and you specify what's called the peripheral subgroup, the peripheral subgroup is, so if you've got your knot, you drill it out of your 3 manifold, right? Then the boundary torus that's left over will be a subgroup of pi 1 of the complement. If I tell you what pi 1 is, and I tell you what that boundary subgroup is, that boundary subgroup that comes from the torus, then that is a complete knot invariant.
So the boundary subgroup is a normal subgroup of pi 1, the overall pi 1?
Yeah.
Can you quotient it out?
Sorry?
Can you quotient it out?
Is it a normal subgroup? I think it should be. Yeah. So if you could quotient it out, and then no, it won't be normal. No, it can't be normal because let's see. Yeah. Yes, it won't be normal in general. Yeah. And I'll talk about cipher genus in a minute here. So what it actually is. This is more just to like show us that we can't just take off the shelf things. You can ask it to draw a diagram instead, and it draws these lovely like diagrams, and but they're garbage if you look at them. So how might you sort of reasonably try and apply machine learning to low-dimensional topology? Well, the first thing is that you've got to sort of like fix a representation of the knots you're working with, and this is actually kind of a non-trivial issue. There are lots of ways to represent knots in a way that a computer can sort of take them as input and then work with them. So one thing you could do is you could sort of specify lattice points inside of R3, and by sort of specifying a sequence of lattice points inside of R3, if you sort of interpret that as a closed loop, you get a polygonal knot. You can also sort of specify a bunch of distinct points on the unit sphere, and if you sort of think of them as having an order, you can sort of think of them as being connected lines. That gives you sort of a jump model for your knots. You can look at random diagrams where you just draw a diagram, and then by sort of labeling the crossings with numbers, and then specifying sort of the label, specifying the ordering of the labels as you go around, that gives you what are called Gauss codes. And then there are sort of other more sort of constrained families of diagrams where you either represent your knot as a closed braid, or what's called a potholder curve, or what's called a pedal diagram. And each of these sort of representations of your knot gives you sort of a way to describe the knot using some sequence of integers or some sequence of vectors that you can then feed into a computer. The problem with these is that they all give sort of a different, when you're dealing with an infinite data set, you have to be kind of very careful when you're talking about what it means by, you can't just sort of sample uniformly from an infinite data set, right? You have to sort of specify some representation or some method for representation, and then when you're sampling now from your data set, you know, the representation that you've chosen sort of plays a role in the distribution that you observe. And so each of these models for representing knots really gives you a different distribution on your space of knots.
But the infinity you're concerned about here is the fact that it can have many artificial overlaps. If I take the right of my moves, I can add an arbitrary number of them to it, and it looks like it moves around in this infinite space.
I would say, I mean, so that's one of the issues. There's infinitely many representations of the same knot type, yes.
Yes, exactly.
But then also there's infinitely many different knot types. Yes. And so that's maybe more, I mean, so for one
is a continuous grading and the other one is a discrete grading.
Well, they're all both, I think they're both discrete.
Yeah, I suppose it's either, yeah.
Yeah. So they're both discrete, and so if you're saying like, so there are a lot of statements where people will say, okay, you know, you might want to say, well, you know, you can talk about alternating knots. So knots that are alternating are knots which possess a diagram that sort of goes over, under as you're passing around, right? You might ask, well, what's the likelihood that a random knot that I produce for you has an alternating diagram? Well, the answer to that question is really highly dependent on sort of what family of knots you're sampling from and sort of how big of a family of knots you're sampling from. And so for example here, well, I'll jump over this for a second, but if you look at knots up to 19 crossings, knots break up into sort of three families. There's torus knots, which are knots that can sort of completely be drawn on a torus inside R3 and a knotted torus. There are satellite knots, which are knots that sort of live inside of a potentially knotted torus. And then there are hyperbolic knots. And if you look at knots up to 19 crossings, and you tabulate, so Thurston proved that every knot is of one of these three types, exactly one of these three types. For knots up to 19 crossings, there are 14 torus knots, there are 380 satellite knots, and there are over 352 million hyperbolic knots. And so when I was in grad school, it was the common knowledge that hyperbolic knots were sort of the dominant, you know, like that torus knots and satellite knots were somehow special knots that don't show up so much. And so, you know,
sorry.
Yeah.
First question is, presumably one is looking for a mapping of the isotopic classes of a knot into some injection of this into some other set.
Yeah.
What is that other set?
That's a really good question. So we want to inject our, so we want to find, like, are you talking like when we're looking for a representation of knots? We want to sort of take our family of all isotopic classes of knots, we want to inject them into some other space that somehow is easier for a computer to, more manageable. Well, the problem is that it's hard to find sort of an injective. So the problem is that we start off, you know, we've got our family of all knots, and we want to map it into some space that a computer can handle. So that's, you know, that's going to be some Rn, right? Or some, I mean, there's other ways. A subspace of Rn, or a subset of Rn for sure.
For example, Jones vector, you get this index of subfactors and so on. Or his original paper was algebraic.
Sorry?
The original Jones paper was algebraic. He started with the Khovanov algebra and quotient, braid group algebra and quotient braid.
Yeah.
So that's quite different from many of these things.
That's true. So you can map it to some algebra or something, or some group structure. But somehow that's got to, like, I mean, I think ultimately these things have to be represented in a computer as, because even if you're representing it as a graph isomorphism type, you'll probably represent it using an adjacency matrix, which can then be flattened to be a vector. So like somehow I think if we're working in computers, everything has to be somehow reducible to something inside of Rn.
There is this Khovanov homology which has come up.
Yeah.
recently. I think you'll be talking about it.
Yeah, I might get to it. I may not. That might be part I don't really get to the Khovanov homology, but you're right. Like, so these are invariants, and ultimately but I think so there's lots of different ways to represent it. The problem is that oftentimes you'll have you don't get like a well-defined map. So every knot, I mean, I guess if you're passing to invariants, okay. So suppose you're passing to some invariant space. Say you're computing the Khovanov homology, or you're computing the Jones polynomial, or you're computing some other algebraic invariant. Then the problem is that, you know, except for some of the invariants that we talked about, like the pi1 with the peripheral subgroup, you're not going to get an injective map, right? Because you have sort of collisions of knots that have the same invariant types. So somehow mapping to some invariants, you don't get injective maps. If you're just looking at a strictly sort of representation, a way to represent your knots manageably, and you're sort of, say, passing to some Euclidean space represented as a vector in a computer, the problem there is that, you know, you have the same knot is going to have infinitely many sort of different equivalent representations. And so you run into sort of issues with injectivity if you're passing to invariants. You run into issues of not having a well-defined representation if you're sort of looking at the knot itself. So,
but there may be some notion of a minimal representation.
There are. So there are minimal diagrams. You can always take like minimal diagrams, but then those are generally not unique either. So there's not really a clean way, and that's one thing that I won't really talk about right now. But it's one thing that I'm really interested in is like what is the most natural way to talk about invariants, or to talk about knots, I should say.
For torus and satellite knots,
Yeah.
can you explain what do you mean by embeddable odd or in like twisted torus?
Okay, so for a torus knot, okay, I've got my standard unknotted torus inside R3. I can sort of trace a curve, right? And this curve can sort of pass around. It's going to go around here. I'm terrible at drawing pictures. The reason I always use slides is because I draw my picture ahead of them. But you can imagine a curve that sort of wraps around the torus n times here as it's going n times here. And so that would be called the nm torus knot. I think I said n the same, but it goes n times in this direction as it's going m times in this direction. That would be an nm torus knot. And as long as n and m are co-prime, that share their GCD is 1, then you get a knot that looks like that. If they share a common factor, then you're going to get a link with multiple components is all. A satellite knot, the way that satellite knots are built is what you do is you take a solid torus and take a non-trivial knot in this torus. So suppose I have something like this, and suppose we do something like this. So see that this thing here, I probably added too many twists, but this thing here may or may not be knotted inside of S3, but as long as it sort of travels around the torus direction, as long as I'm sticking it in the torus, it's not trivial, it's a non-trivial knot, okay? And so then what I do is I pick a knot like this, and I think of it now as being thickened, okay? And now what I'm going to do is I'm going to take this torus, and I'm going to glue it along the bound, I'm going to glue it along this thing, so I get some like knot that lives inside of here with a bunch of twists. I'm not drawing it very carefully, but you get some non-trivial knot that lives inside of some knotted torus. That's what a satellite knot is. Is that okay? Did that answer your question? Sure. Okay.
Can you ask one?
Yeah.
You say hyperbolic knots?
Yeah.
Because the complement is a hyperbolic metric.
Yeah.
But may also admit other metrics like flat metric.
Yeah, because
which one?
so it does admit like it admits like a spherical metric because it's a subset of S3. But Thurston shows that essentially, like, you can, essentially, Thurston shows that, like, the existence of a
unique metric.
yeah, the existence of one of these negatively curved metrics, these hyperbolic metrics, is kind of reliant on the fact that there's not any, like, tori, non-boundary parallel tori floating around. And so in a satellite knot, you get precisely one of these tori, you know, comes from this, like, this gluing operation. So that's why satellite knots don't have a hyperbolic metric on the complement. And then torus knots have, I erased it, but torus knots live on a torus. And so they have sort of, I guess, two tori that violate sort of Thurston's conditions. So yeah. So the sort of the punchline of this slide is that essentially, like, you know, we thought that sort of, at least when I was a grad student, I thought that this is sort of like the trend that continues. But, you know, in 2019, it was proved that essentially the proportion of these things don't go to 1 as n goes to infinity, or the number of crossings goes to infinity. But essentially, the number of satellite knots has to sort of, I think the number of satellite knots in the end sort of has to dominate. You can kind of make some more precise statements like that. And so you really have to be careful about making statements about, like, random knots or families of knots or the probability. You can maybe make sort of statements involving asymptotics, but you have to be kind of careful. And so this is kind of jumping back to this. The other issue is that oftentimes what we want to study is we want to study invariants of knots, but these invariants are highly discontinuous with respect to the distributions we're looking at. What do I mean by that? I mean, I can give you, like, I can represent a knot using one of these representation methods I showed you on the previous slide, but if I change one piece of information in that description, I could sort of dramatically alter what the invariant values look like. So for example, for any knot, I can give you sort of any knot, and by sort of messing up the diagram enough, you can find a crossing that can be changed, which changes the bridge number an arbitrarily high amount. Now, I didn't say what the bridge number was, but essentially what this is telling you is that at least sort of with respect to invariance, knots are kind of a really, everything's highly discontinuous, because you can sort of change crossings, change one piece of information, and all of a sudden the invariants you're looking at sort of change drastically. So, so these are all sort of things that have to be sort of kept in mind when you're trying to sort of throw techniques of ML at knot theory. But maybe I'll pause there before I get into some, like, more concrete case studies and actual invariants. But any other comments or questions?
So, I mean, you just gave a 3 broad categories.
Yeah.
Presumably you can divide those categories into finer ones. That was Thurston's classification.
Oh, into the knot types?
Yes. You can presumably split the hyperbolic into a subcategory, set of categories.
Yeah, I mean, there are, so for example, there are definitely families of satellite knots that you can look at. There are definitely, like, smaller families of, like, hyperbolic knots you can look at. I'd have to think a little bit about, like it seems like once you have this broad 3, you know, like this triple classification thing, within each of these families there are, like, you know, say pretzel knots, and there's infinitely many different pretzel knots, and there's infinitely many different, like, you know, whitehead doubles and stuff like that. But there
may be one of those that dominates. And
that is true. I don't think, though, like, for example, like, I'm not aware of any way of, like, for example, taking satellite knots and then breaking it up into a classification where every satellite knot has to be one of these 4 things. Like, there's families within here that are sort of well studied, but I don't know that they actually completely classify all satellite knots or anything like that. It's a good question.
May I ask a naive question?
Yes.
It's I know if you're sitting in the lecture room, it sounds like God is talking to you. Is a Mobius strip of any significance or interest to knot theorists?
It is to me. You can, Mobius strips. Well, so there was a question a little bit earlier about cipher genus. And maybe I'll just, maybe when I get to cipher genus, I'll diverge a little bit and talk about the Mobius. I'll answer maybe your question about Mobius.
Okay,
But it'll kind of
thank you.
lead into that. If I forget, don't forget to like don't be afraid to like hold me to that. Sometimes I promise that I'll talk about things later on and then I forget to talk about them.
Okay,
I'm
thank
not
you.
trying to dodge your question. Oh, but here we're at cipher surfaces already. So one of the families of invariants that I'm interested in studying are surface invariants for knots. So one way of studying knots is by looking at the surfaces they bound. So here, for example, I've got two knots. I've drawn two knot diagrams, and then you can imagine sort of filling them in with surfaces so that the knot is the boundary of the surface. And typically people study orientable surfaces. So, for example, the unknot is the only knot that bounds a disk inside of 3 space. So the unknot can be characterized by the fact that it bounds a disk, whereas the trefoil and the figure 8 knots, which I've drawn here, they both bound punctured tori. So it's kind of weird to think about, but there's some way of taking this torus and sort of re-embedding it inside of S3 so that the boundary is a trefoil and the boundary is a figure 8. Okay, and I'll show you some concrete examples in a second. So to your question about Mobius, so to your question about the cipher genus, the cipher genus is the minimal genus of a surface embedded in S3 whose boundary is the knot that we're looking at. So for example, and I think I have a slide of this in a second, the unknot is the only knot with cipher genus 0. It's the only knot that bounds a disk. Whereas the trefoil and the figure 8, these two knots down here, they have cipher genus 1 because they both bound embedded genus 1 surfaces. Is that okay? And then to your question, Mobius bands, you could remove the orientability condition and say, okay, I don't, cipher genus, whenever someone says cipher genus, they're talking about orientable surfaces. You could say, well, hey, I don't care if it's orientable, can you classify all knots that bound, say, Mobius bands? You can, and it turns out that knots that bound Mobius bands are precisely, we've talked about satellite knots. I won't be able to draw this on the fly. Let's see. Trying to draw a Mobius band that's been knotted somehow. And I'm going to get into trouble. So let's try it like this. And I always somehow seem to do this where I run into, okay. Okay, something like this. So here's a Mobius band. I didn't actually count the twists. I may have added one too many twists. But this Mobius band, if you bound an embedded Mobius band, then it turns out you actually have to be a satellite of some very standard form. So people do study, instead of, if they drop the orientability condition, they can study what's called the cross-cap number, and the cross-cap number is very much like the cipher genus. It's just what's the simplest non-orientable surface bounded by the knot. In which case, sort of the analog to bounding a torus would be sort of the simplest non-orientable surface, the Mobius band. And it turns out we can classify knots that bound Mobius bands quite easily.
Any non-orientable surface has a 2-fold cover, which is orientable.
Yes.
So can I lift the knot on the non-orientable up to the covering surface and study it there?
Okay, so look at the boundary. Okay, so take the 2-fold cover. And yes, and actually I have a paper with a colleague where we classify immersed Mobius bands. So these are Mobius bands with sort of certain types of self-intersections. And one of the ways we study it is we try and use this annulus theorem, and there's this disk theorem that we try and use. And in order to sort of get it to work, we have to sort of lift to a double cover of the knot, and it takes the non-orientable surface to an orientable surface. So yeah, that's definitely a very reasonable thing to do if you're trying to work with these things. If you somehow want to take something in the non-orientable realm, turn it into something orientable, that's a very reasonable thing to try. Yeah. Maybe not reasonable, but we tried it and it worked. So I mean, it's something. So here's an example. Here's the knot 6-1. It's called the stevedore knot. it bounds a punctured torus, and I tried to sort of draw this in here in gray, so I've got this sort of twisted ribbon that goes around sort of and twists a couple times, and then I have this sort of this little ribbon that I've attached with a half twist here and a half twist there. If you count the number of like intersections, or if you count sort of the number of, you can sort of break this up into a bunch of ribbons and discs, and you can actually see that this is homeomorphic to a punctured torus. So that tells me then that essentially the stevedore knot also has Seifert genus 1. But the Seifert genus is a very classical, well-studied invariant, and you can actually compute the Seifert genus on the nose using what's called Hughes-4 homology, and there's, I guess, some other techniques as well. But there's sort of a related invariant that I think is a little bit more interesting to four-dimensional topology called the slice genus of a knot. And what the slice genus of a knot is we sort of think about the S3 where our knots live as being the boundary of a four-ball. And so I think of my knot as living inside the boundary of this four-dimensional ball. And I can imagine a disk that sort of fills in my knot, but where instead of making sure that that disk lives inside of S3, I'm allowing my disk to be inside the four-ball, okay? So I'm essentially giving myself one extra dimension to play with. Okay, so if this disk is smoothly embedded and the boundary of my disk is equal to the knot, or sorry, I shouldn't say disk, it can be a surface with positive genus. So if my surface F is smoothly embedded and the boundary of my surface is equal to the knot, then F is called a slice surface for the knot K. And the slice genus of my knot is just the minimal genus of any slice surface whose boundary is the knot that I'm looking for, okay? So the slice genus is this sort of captures, it's sort of a measure of complexity of the knot in some sense, and it sort of is measuring how, if I take my knot and I want to fill it in with a surface that dips into the four ball, what's sort of the simplest topology type of that surface that I'm looking at? So questions there on what the slice genus, or sometimes people call it the four-ball genus, or so if you haven't thought about surfaces inside a four-dimensional space much, how do you represent a surface in four-dimensional space? Well, sort of the most natural way, at least, is by sort of taking a family of level sets. So I sort of think of my surface as being sliced by a family of level sets, and by sort of representing the intersection of my surface with these level sets at enough intersections, I can represent my knot. And so I think of sort of a slice surface as being sort of really just a way of taking a knot and deforming it down to something trivial. So for example, here's the stevedore knot. I can imagine building a surface starting at the boundary of S3 and sort of pushing into the four ball. And as I'm doing this, I sort of see a little kink appear. These two little bands come together. And what I'm going to do now is I'm going to add a saddle point in my surface. So I've added a saddle point. Now if I look at, I have two distinct components, a red component and a blue component. I can sort of pull them out from each other. And now what I'm going to do, because I have two unknotted, unlinked components, I can cap them both off with disks, and they disappear, and now I have a complete surface, okay? Now, if you compute the Euler characteristic of your surface, you count the number of saddle points, the number of local minima, local maxima, you can compute that this thing was actually has sorry, excuse me. This thing has Euler characteristic 1. Therefore, it's a genus 0 surface. It's a disk, and therefore the slice genus of this knot is 0, and therefore 6,1 is a slice knot. Okay. Now, why might you care about slice knots? So this you asked, I think, a question about constructing exotic smooth structures on R4, right? A week ago or so. It turns out that understanding the slice genus allows you to construct things like exotic copies of R4. So there's a really nice hands-on construction where you build, you can show that you get exotic copies of R4 using knots who are topologically sliced, so they bound locally flat topological disks, but they don't bound smooth disks. So that's one way to sort of construct exotic R4. Another sort of reason why slice genus has sort of gained a lot of interest in it's really sort of something people are interested in, is, we have in low-dimensional topology, there's the smooth four-dimensional Poincare conjecture, which says that the only smooth structure on S4 is the standard smooth structure. Now, we have no way of really, I think this conjecture is still pretty far out of reach of us. It's possible that there's a unique smooth structure on S4, but then it's also possible that there are, infinitely many smooth structures. One way of constructing potential counterexamples, so potential exotic structures on the 4-sphere, is by sort of finding knots with sort of, with sort of pre-specified properties involving their sliceness. So if you can find a pair of knots that have the same zero surgery, where one of them is sliced and one of them is not sliced, then you can construct counterexamples to the smooth four-dimensional Poincare conjecture. So this is sort of like really one of the only techniques, or one of the only viable approaches that we have right now, because there's not a lot of invariants on smooth 4 manifolds that can be used to distinguish homotopy 4 spheres. So, yeah.
In 3D,
Yeah.
there are prime manifolds.
Yeah.
And by connected sums of prime manifolds,
Mhm.
I can get all possible closed manifolds.
Yes.
And there's a corresponding thing with links. I suppose your links are oriented links. I don't know. I suppose.
Okay.
When you write, I suppose there's an arrow on the links.
You can, you can orient your links.
You can write connected sums of links, because you can cut it and join at those points. And many of the things you're writing should have nice behavior under this connected sums of links. Do you know anything about it?
About connected sums of links?
Yes.
Well, connected sums of links is a little trickier than connected sums of knots, because it's not well defined, right? Like, you have to specify what link component
It depends upon where you cut it and join it.
Yeah.
That I don't know.
Yeah. So a lot of invariants have well understood sort of behavior under connecting sums. So like a lot of invariants, you could, if you gave me the sort of the invariant values of the link, and then you sort of specified what connect sum you're taking, you'd have a nice relationship between the resulting link. So yeah, I think there's nice relationships.
So there is no analog of prime manifolds for links.
There's no analog of prime. Okay, so I see what you're asking. Sorry, I misunderstood it first. I honestly don't know. I would need to think for a minute or two about that. I haven't really seen anyone. I haven't thought about it at all, and I haven't seen it anywhere.
We have also not.
Okay, I mean, you could imagine sort of like, you could imagine decomposing every component into a connected sum of prime knots, but then the sort of but then there's linking in between these different components, and how you decompose the components into prime knots is gonna be different depending on how you like the linking that you end up with is gonna be different depending on how you decompose it into summands. So it would probably get pretty dicey pretty quick. I can see maybe some problems with that. Essentially the problem with the slice genus. So the slice genus is at least to low-dimensional topologies, it's an invariant we'd like to understand much better. The problem is that in order to compute it, there's sort of 2 steps that you have to do. First of all, you at least sort of one approach would be, you have to sort of find a surface, explicit surface, which realizes the minimal genus. So you have to sort of prove that the slice genus, there is a slice surface of genus 1, for example, and then you have to prove that there's no slice surface with genus any smaller. So you sort of need to explicitly construct a knot with a given genus, and then you need to, a surface with a given genus for the knot of interest, and then you have to prove that no smaller genus surface exists. Now, to prove that no smaller genus surface exists, we have sort of relationships that come from invariants. We have lower bounds that come from invariants. But there are lots of knots of very reasonable size for which we don't know whether the slice genus is like 1 or 2, or whether it's, say, 0 or 1 or something like that. Where like the best surface we've constructed doesn't meet the best lower bound we have. And so the question here would be, this is maybe an area that's sort of ripe for for trying to throw machine learning at it. So one approach would be to try and use, say, supervised learning. And so this is sort of where I got interested in this approach here. And so in 2016, I was sort of thinking about, hey, is it possible to sort of predict the slice genus of knots? And so taking sort of this data set at knot.info, you can sort of take all the knots and you can represent them as vectors, and you can sort of see if a neural network can predict the slice genus very accurately. So it turns out that neural networks are pretty good at predicting the slice genus of a knot using a braid representation of the knot together with a few invariants. So it turns out that the sort of the initial experiments we ran were able to predict the slice genus with like 93% accuracy. And if you sort of look at the invariants that knot.info had, and you said, well, what would be my best guess if I just looked at these invariants and I sort of understood the relationship between these invariants and the slice genus? The sort of the best guess that you're going to get, or the best you can do in that way, is about 71%. So it does a lot better than the neural networks are able to learn some information a lot better than just sort of what's contained in the invariants. It turned out that since that time we've discovered a bunch more slice genuses using sort of more other techniques. And it turns out that these predictions were continue to be pretty accurate. I think what's most interesting here, though, is that the neural net did not provide clear predictions for all knots. Okay, so if you look at sort of if you write down a table of all the knots where we don't know the slice genus, and you plug them into the neural network, and you say, well, hey, how well does the neural network do, or what are the predictions the neural network makes? Notice that for all of these knots here, it predicted 1. But for this knot right here, 11N34, it sort of predicted that the slice genus was like right at, was like right at 0.5. And this was a knot, this was kind of a famous knot called Conway's knot, where we didn't know if it had slice genus 0 or slice genus 1. And for some reason, all of the other unknown knots the neural network was able to predict really well, or was able to make very confident predictions. But for Conway's knot, it was like smack in the middle, 0.49. Okay, and
have you been able to check that these are correct ones?
Yes. So most of these are correct. They're part of those. I think I forget how many, like 600 or whatever knots that were knots that we have since that time computed the correct slice genus to, and these were a part of that, and the accuracy on that data set was like 96, almost 97%. So these particular ones what's that?
Good but not perfect.
Good but not perfect, and that's why so I'll talk about how do we make these perfect. So this Conway's knot, I gave a talk of this actually here in Dublin. The first time I spoke about this was actually just at Trinity. They had a Hamilton workshop there, and I gave a talk on this. And the first question the audience asked was, well, what does the neural network predict on Conway's knot? And so of course at 0.5, it makes very sort of indecisive guess on Conway's knot. And so if you sort of do a lot more work and you construct sort of, there's this relationship called concordance. Essentially, I constructed about 10,000 knots that are in the same concordance class as Conway's knot, and therefore have the same slice genus. If you generate a bunch of other knots that will have the same slice genus, and you sort of compute the predictions on those knots, the neural network sort of slightly leaned towards, on average, guessing that they had slice genus 0. However, Lisa Piccirillo in 2018, about a year later, famously proved that the slice genus of Conway's knot was equal to 1. And so this is sort of like, to a knot theorist, this is the most intriguing part. Like, I mean, we just plug things into neural networks, but the question is, why did it struggle so much with this Conway's knot that had all these interesting topological properties? And so that's one of the big questions that we're still trying to like really understand, or I'm particularly trying to understand, is like, what was it about Conway's knot and that mode of failure that sort of made it so that it was so hard to predict the slice genus? Maybe in the interest of time, since I've already gone a knot, I'm gonna maybe kind of switch gears a bit, and I'll talk a little bit about, I'll talk about reinforcement learning and maybe like some more speculative stuff for just like a few more minutes here. So Well, any comments or questions before I switch gears? Sorry?
Just a quick question.
Yeah.
You're talking about these different representations
Yeah.
of knots. Do they impact the accuracy or performance?
They do. And that's what, yeah, so everything I did here was using braids, like braid representations. We've run experiments using like Gauss codes and other things like that, and not exactly for these experiments on the nose, but like other similar experiments where we're trying to predict things. And the way you represent the knot does matter. So, yeah, so for example, Sergei Gukov and Jim Halverson and Fabian Ruhl and Ciprian Manolescu have this paper where they're looking for ribbon disks. So these are like slice disks, but they have a special additional property. Essentially, there was this big family of knots that Ciprian and Lisa Picarillo came up with that would, if you could prove that any of these knots were slice, then you could find counterexamples to the smooth four-dimensional Poincare conjecture. So these were these knots that everyone really was interested in, because if we could prove that any of them were sliced, then we'd sort of have a counterexample to the smooth four-dimensional Poincare conjecture. And they came up with a way of constructing minimal genus slice surfaces using reinforcement learning, using sort of one method of representing knots. I worked on kind of a parallel project with other ways of representing knots, and their technique, they chose a different method of representing knots. They were able to sort of handle much higher crossing knots than we were able to handle. We were able to handle pretty large crossing knots with some modifications anyways, but yeah, so just long story short is like the way that you represent a knot does make a difference, and it sort of is borne out a few times. And so that's the question is, well, one of the problems you have to answer before you make this approach is you have to say, well, this is the problem I'm trying to answer. What is the most natural way to represent the knot with respect to this problem I'm trying to solve? And the answer to your question could be very different depending on what the problem you're trying to approach is.
Can I ask you a question?
Yeah.
Suppose I take two random knots and give it to a Turing machine.
Yes.
Will there be a haunting problem?
To detect when they're isotopic?
They're isotopic or not, for example, or any other such problem.
Yeah, so
How do I know these are decidable problems?
so like for example, the unknot recognition problem is decidable.
Is decidable.
Yeah.
But there are no invariants I know which separates the unknot from the other knots.
Well, yeah, so Khovanov homology detects the unknot.
So, I see.
Yeah, and Khovanov homology detects a number of knots. There are a number of knots where we know sort of the Khovanov homology of that knot is unique. And Heegard-Floor homology also has similar properties. Maybe I'll use that as a segue into maybe the last thing I'll talk about. Well, I'll maybe just say a few things about reinforcement learning, then I'll talk about this question of like, are there invariants that we can use to sort of separate the end knot from other knots? So reinforcement learning is kind of it's another sort of branch of machine learning, and essentially what it deals with is it deals with this problem of like finding optimal solutions through large intractable search spaces. So the setup for like a reinforcement learning problem is what's called the Markov decision process, where essentially you have this setup where you have sort of some set of states S, and you have some collection of actions A, okay? Now each action A, you can think of it as a function which sort of takes a current state and sort of evolves it into an updated state, okay? So I think of my actions as acting on my states, given a state and an action, the action acts on the state and turns it into a new state, and given every state action pair, we have an associated reward, which is some real valued scalar. And so you think of a reinforcement learning agent as kind of like, essentially your agent is Mario here. Mario is on some level of the game, takes an action, does something, gets some reward, right? And in performing that action, it evolves the state into a new state, and it earns Mario some reward. Then Mario takes a new action, and so on, and so on, and so on, okay? And the goal of reinforcement learning is to find essentially an optimal decision policy. Meaning, given a state, if I'm in a current state, can I come up with some rule or some function that's going to tell me the optimal action to take given the state that I'm in. Okay? Now, and what I want to do is that the objective is that when performing these actions, I want to sort of obtain, I want to maximize some reward, some cumulative reward. Okay? And so what a neural network, or sorry, what a reinforcement learning agent is doing is it's trying to essentially learn optimal decision policies to maximize some reward function or some objective function. Okay? So there's sort of a whole framework for dealing with this where you, given a state and an action, you have what's called a value function or a Q function or something related, where essentially your Q function is just measuring, you know, if I'm in state S and I perform action A, and then I perform the best possible sequence of actions after that, what is my estimated, or what is my expected cumulative reward? Now, if you can measure this, or if you can estimate what these Q values are, so this Q function takes in a state and an action, and if you can somehow measure that, what that's going to tell you is if you're in state S and you perform action A, what's the expected reward for doing that? Well, if you can compute that, then that gives you an optimal decision policy, because if you're in state S, all you have to do is plug in all available actions and then pick the one with the highest Q value, because that's going to be the best action you can take. And then you get to a new state, plug in all the available actions from that new state, pick the one with the highest Q value. So fortunately, there's sort of an iterative update law for Q values based on Bellman's equation. And so this reinforcement learning framework has been sort of around for a while. The problem is that if you're dealing with a reinforcement learning problem that's where the state space and the action space are relatively small, you can essentially just sort of just start with random initialization of your Q values, and by sort of performing enough actions in different states and exploring your state action space enough, applying your iterative update to your Q values are going to converge to the correct true Q values. So sort of there's theoretical guarantees that by performing this and iterating enough, you're going to find estimates of your estimates are going to converge to the correct Q values. The problem is most of the state action spaces we care about today are very large, much too large to record using sort of a table. So instead what we do is we train a neural network to predict the Q values. And now, because we're introducing a nonlinear approximator, we lose convergence guarantees. And so this brings us into deep reinforcement learning, which can be done quite successfully, but is also a lot harder, I think, to implement in practice. But
there's no Monte Carlo step in this.
Oh, so there is ways to there's ways to sort of add randomness. So the way that I've posted it here, every state in action gives you a well-defined state, but in a lot of there'd
be local wells in the state space that you're likely to get trapped in.
Yes, you definitely can. Yeah. So I'm not sure. I may have misinterpreted. So there's definitely local wells you can get trapped in. Yeah. So
there's an accept reject step where you say I toss a coin and I will accept this even if it's less favorable. That's the Monte Carlo step.
Yeah. So there's this trade-off between explore and exploit, exploitation and exploration, where in any reinforcement learning framework you have to you're sort of exploring the state space pseudo-randomly in some regards. So at first you're sort of with some coin flip, you're deciding, okay, am I going to take a random state, or am I going to follow what my current policy is telling me to do? Now you do want to follow your current policy a certain amount, because you want to then be able to sort of strengthen the policy and improve it. But you also want to explore new regions of the search space. So typically there's sort of a coin flip, and initially you're going to explore a lot, and as you sort of progress along your training regime, you're going to explore a little bit less and a little bit less until essentially you're mostly following your policy with some exploration. mixed in. Is that what you were kind of referring to?
Yes, but I mean, in simulations and in field theories and things like that, what you in lattice models, what you do is you still accept ones even though it was a less favorable state.
Yeah. Yeah.
That helps you to climb out of wells.
Yes. Yeah, and you still want to do that because at every state of the game, your current Q value, let's say we're doing Q learning like this, your current Q values are merely an approximation of what you think are the correct Q values, right? And so your approximation could be off. And so it's quite possible that you have something that locally looks like a bad decision, but it's a necessary step for a much more improved policy. Yeah, and so that's why exploration comes in, is because you want to be exploring sufficiently well, you want to explore sufficiently often so that you don't miss out on action sequences that look bad in the short term but are beneficial long term. Yeah. Is that okay?
Yeah.
Yeah. So okay, so I'll just the one thing I'll say is that we can apply this framework to constructing slice surfaces, minimal genus slice surfaces. I'll just jump to this picture here. This is all stuff that is related but not necessary. So the thing is suppose I start with a knot like this, and I want to sort of construct a minimal genus slice surface for this knot. Well, if I sort of think of it as a closed braid like I've drawn it, I can think of each step in constructing my surface as being one of a finite number of actions. So for example, I can add a local maxima here, which creates a new component. It's hard to see that this is gray, but I can sort of undo a crossing, which would be a saddle point. I can sort of isotope my knot around, which doesn't modify the surface at all. And I can kind of construct my surface through a sequence of very simple local operations, okay? So I can think of my local operations as being my actions, and the current diagram as being my state, and now I have sort of a Markov decision process, where given a state, I have to decide sort of what the next action is, okay? And as I'm building this surface, adding saddle points is going to decrease my reward by 1, whereas adding components like this or capping off components like this is going to increase my Euler characteristic by 1. And so if my goal is to minimize the genus, really what I'm looking for is I'm looking for a sequence of operations like this, which simplifies my diagram down using as few saddle points as possible while having as many of these components being capped off as possible. And so it turns out you can kind of construct a Markov decision process and throw reinforcement learning at a problem like this. And it turns out that you can, sweeping some details under the rug here, but it turns out that you can construct sort of, we kind of do something slightly different where we're building quasi-positivity and we're checking for band, but forget that for now. It turns out that we can handle some fairly large grades using sort of this reinforcement learning approach, okay? So this is kind of an improved approach, I think. Like the supervised learning is interesting because it makes guesses, but at least on the mathematicians, you have a hard time selling this stuff to a mathematical audience if you're just saying, hey, we're making predictions and we're getting pretty good accurate steps. What a group of mathematicians wants is they want something where you can sort of can concretely prove that the knot of interest has this property or does not. By using reinforcement learning, when we're sort of building these action sequences, this gives sort of a very concrete way for a mathematician to check that yes, this knot does have the property that you're claiming it does. And so I feel like sort of reinforcement learning offers a lot of sort of promise in terms of generating like concrete things that mathematicians can sort of check by hand actually work, okay? Another place where reinforcement learning can be done is like involving like counter. Oh, I should just say this is from Ciprian from Ciprian and Fabian Jim and Sergey's paper. This is just sort of mentioning the other setup they use. They construct things quite differently, but they get some really nice results here. So The last thing I'll talk about is just like maybe using reinforcement learning to like look for counterexamples. Okay, so this is the question of like Khovanov homology detects the unknown, right? So Khovanov homology is this beefed up version of the Jones polynomial, I'm going to sort of assume that most of you are familiar with the Jones polynomial. It is sort of, you know, has had a fairly big presence in physics. The thing about the Jones polynomial is we know the unknot has Jones polynomial 1, but we don't know if there's any other knots that have Jones polynomial 1. Okay, there may be non-trivial knots that have trivial Jones polynomial, but we simply don't have a way of checking that. So the Jones unknot conjecture asks, or states, that if a knot has trivial Jones polynomial, then that knot has to be the unknot. For Khovanov homology, that statement is correct. If a knot has trivial Khovanov homology, then it has to be the M-knot. For Hughes, there's a bunch of, you know, other sort of categorifications of invariants that do detect the unknot, but we don't know whether the Jones polynomial does. And so the Jones unknot conjecture has been checked for knots up to 24 crossings, and that involved checking, say, 59 trillion plus knots. So this is a major sort of computational undertaking where they, you know, ran a bunch of parallel computers, and I mean, it was sort of the engineering, I think, was they had to think very carefully about sort of taking the knots and breaking them up into these certain tangle diagrams and sort of like simplifying the computations there. But to just verify up to 24 crossings involved 59 trillion knots that had to be checked. Now,
if I go to 25, how does it scale?
Well, that's so knots increase like exponentially with crossing number. So I don't know the number of 25 crossing knots that would have to be checked, but essentially we're kind of at the limits of where I think we can reasonably use classical techniques.
The coefficient is large.
Yes. Yeah. So.
Each of the 24.
Yeah. So can we use something like reinforcement learning to try and produce counterexamples instead of sort of searching for them naively? So this is sort of a speculative work in progress. I'm going to announce right now we do not have a counterexample to the Jones-unknot conjecture, just in case any of you were sticking around for that eventual punchline. But one way, thank you, Venus. One way you could do it is essentially, so here's one way. There's actually lots of ways you can phrase this. Here's one way to do it, is if you look at what are called potholder diagrams, every knot emits a potholder diagram. So a potholder diagram is just something that looks like this, where I'm allowing myself to change the crossings in any way possible. But every knot that you pick can be put into a diagram of this form. Now, once your knot is in a diagram of this form, you can represent it entirely as just a bit string, zeros and ones. Okay? So one thing you can do is you can phrase this as a reinforcement learning algorithm by basically saying, okay, what I want to do is I want to my states are going to be my potholder diagrams. My actions are going to be changes that I'm making to my potholder diagrams. So, for example, maybe I want to change, you know, this is my current state, but maybe I want to change that crossing there. So I change one of the zeros to a 1 or something, okay? So I get a very well-defined state space that are just bit strings. I get a well-defined action space that's just changing any of the individual bits. And essentially, without getting too much into the invariance, essentially what we're going to do is we're going to break it up into 2 stages, where in stage 1, we're starting with a random diagram, and then we're going to throw a reinforcement learning agent at this diagram to try and make as complicated a knot as possible. So essentially, we're going to try and find a knot where I'm going to use the signature as my reward function. So essentially what my reinforcement learning agent is trying to do is basically to find the knot with as big a signature as possible. And by doing that, it's going to be forcing the unknotting number to be really high. Then we're going to sort of collect a bunch of these individuals, these knot diagrams we've created where we know the unknotting number has to be very high. And then we're going to repeat the process of unleashing a reinforcement learning agent on this knot diagram. But now the reward function is going to be based on the complexity of the Jones polynomial. So what my reinforcement learning agent is now trying to do is it's trying to simplify the Jones polynomial of the knot without actually unknotting the knot, okay, or untying the knot. Now, it turns out that each of these stages, it can kind of do these, it can do each of these stages and kind of achieves each of these stages. But, you know, in grids up to like 7 by 7, what ends up happening is that, you know, it creates this knot with really complicated, with really high signature, and then when it tries to basically simplify the Jones polynomial, it can simplify the Jones polynomial, but it takes too many steps to do it. And so it simplifies the Jones polynomial, but it also simplifies the knot at the same time. So, so that's one approach. There's a whole family of examples where you can kind of like really take a problem that is, you know, a knot theory or low-dimensional topology problem and frame it as a Markov decision process. And so somehow if we could sort of like, somehow it seems like a lot of what mathematicians care about, or at least in low-dimensional topology, can really be kind of like oftentimes turned into Markov decision processes. So I think it's like a really, you know, really low-dimensional topology in particular, I think, is really sort of right for some of these techniques. But I've been going for a while, so I'll stop there and take questions. I do have a thank you slide. I like didn't know how many questions there'd be, so I had lots of like slides that I put in here, but here we go. There's thank you. There you go. Those are knots. Anyway. That's the Gordian graph of knots. So like this Gordian graph is like every vertex of the graph is a knot type, and two knot types are related by an edge if you can find a diagram of these two knots that are related by a single crossing change. So if I can get from this knot to this knot by a crossing change, they get connected by an edge. So we have this nice infinite valent or infinite degree graph. And this is not the whole thing, obviously, but that's what that picture is, if you're wondering.
Let me ask you, do I understand that every knot can be mapped to a binary code, like 0, 1, 0, 1?
Yeah.
Then the binary codes are simply representations of qubits in quantum computing.
Yeah.
So there, is it that a given knot might have a huge number of them? I don't know, but it is something that these binary codes are understood as C2 to the power of n or something. And one knows there are metrics on this space. What is the shortest distance between two and so on? Already from the quantum information people.
What is the shortest distance between like two bit strings that represent?
Yes.
Is it possible to find that?
It is known. It is in published. People here doing quantum information would know. The Fisher-Rao metric, and so you know this stuff.
I have heard of it, but I don't really know it.
Yeah.
The Fisher-Rao
There are many. There is a whole group of people working on this from the quantum information side.
Okay.
So the one metric that I am familiar with because my friends use it, it's called the Fisher-Rao metric.
Okay.
But there are other metrics also, metrics don't. But so the information, how do I go from one binary sequence to another one? What is the shortest path? How many steps? For example, you can define a metric number of steps I have to take to go from one to the other. This is sort of known. I think it is sort of known. So I am wondering whether this, why don't you say that you solved the knot problem, because I can map it to a binary code.
And then use like the quantum information theory.
So it's a unique thing. So can I go back? No. What do you want? What mode do you want? You have classified all the knots.
Well, every knot can be represented as a bit string, but those bit string lengths, I mean, obviously, like not in a uniform length.
There's no, a bit string is not going to be a unique prescription of that knot.
Yeah.
Bit string is an injection.
It's an injection, but it's not an actual knot.
Yeah, so from knots to bit strings is not a well-defined map.
It is not.
Yeah, it's not well-defined. So you.
But there is a map. There are many maps. That's what we mean.
Yeah. Well, like every knot has infinitely many bit string representations.
That I don't know.
No, it's true. It's true.
It's the same as all of your other ones you've I think you've essentially told us that. You can always add crossings
Yeah,
that do nothing, which adds zeros and ones.
yeah.
Doesn't have a unique length even as a string.
But in quantum theory, this is like adding backward. Go on tensoring some qubit string, go on tensoring with vacuum, nothing happens. No?
But it's not tensoring with vacuum. It's tensoring with things that aren't obviously vacuum. They're ones and zeros.
So plus and up, down.
Yeah, but you might have two crossings that you added, which you remove with the next two, or somewhere else along the line. So that
Let me
the
have
most
go
is
back to
nothing.
question,
Yeah,
which I think maybe you did not answer.
sorry.
Is this a solvable? Is this a decidable proposition?
Decidable proposition of determining when two knots are isomorphic.
For example,
Yeah.
I formulate some problem like I give you two random knots, okay, and I don't know how to do it, but can I put it in a Turing machine and will it halt?
You could ask the question. I mean, in the context that you're doing that, I think he can take his polynomial diagram, which is back to ones and zeros, but now you have to remove anything that is eliminated by trivial Brigham-Eisenhower moves.
Yeah.
Because obviously the way he has drawn it, it's subject to Brigham-Eisenhower moves. To get to go map it to a new polynomial. And is that decidable?
Yeah.
I mean,
So he didn't
if I didn't have to go up to infinity, it probably would be.
Yeah, and there are families of like the tricky. So like for example, the unknot recognition problem. I mean, first of all, you can compute the Khovanov homology, and you can detect if it's the unknot or not. But there are like algorithms for like finding Reidemeister sequences from a messy unknot to the unknot. The problem is that they do require sort of complexifying before they can be completely simplified. So there's not, and I think there are like bounds on the number of like Reidemeister moves between, given a diagram of the unknot with n crossings, it can always be reduced to a diagram of like the trivial diagram using something, but it's some terrible bound. So these things are decidable, but oftentimes they're not. There's no real practical way to implement them. But a lot of these questions are yes, decidable.
So it's
But the slice genus is not.
It's known that there is a maximum number of Reidemeister moves that you would have to go through.
Yes. Yeah.
This is only for the unknots, or is it known for all knots?
So this is due to I think Mark Lackenby, and I should be careful. I don't know if it can be strengthened to work for any two diagrams of a knot. It uses. I should be careful about what I say too much on if I'm being zoomed and recorded. But afterwards I can look up the reference. I can find the reference for you. But I don't know that it necessarily works. It may or may not work for other knot types. It certainly works for the other knot though.
So just another question. In three manifolds, there is a test and volume conjecture.
Okay.
Is there any analog of that for knots?
The Thurston volume conjecture. What is that conjecture?
From what I understand, if there is a preferred volume you can associate. So preferred.
This is a hyperbolic volume, right?
Yeah.
Hyperbolic. So first thing I understand is that we can get all three prime manifolds by quotienting the appreciate of the hyperbolic by discrete subgroups of SL2C.
Yeah.
That's what I understand. Then apparently this is what is used by
Okay, so the geometrization conjecture.
Ah.
Oh yeah, where all geometries, all three manifolds decompose into primes that all have a fixed geometry, that all have a certain finite type geometry. Yeah. So is there like a geometrization for knots and links? I don't see an obvious analog. I'm not aware of an obvious analog to like Thurston geometrization. because so like you could maybe ask something about like the not complements, but the not complements, I mean the not complements already have a very like, I mean, I guess maybe the analog to Thurston geometrization is just captured by Thurston's sort of, you know, classification of knots into one of three types, where the complement of the knot is hyperbolic, or it's a satellite knot, or it's a torus knot. If you were to look at knot complements, then I think that's kind of would be the analog. But for all these geometries that Thurston comes up with, like most of them don't show up in the list of, most of them can't be knot complements. So it's like if you try and like phrase a Thurston's geometrization using the complement of the knot, most of the things that show up in Thurston's geometrization wouldn't show up as a knot complement.
See, what is very puzzling to me is that you have got given an analysis of this, but part of field theory as well, which is derivation of the images. Those polynomials was using part of field theory. Then I have also listened to seminars by him where he was trying to get the Khovanov homology by using quantum field theory. So at that time, I remember asking him what happens to connected sums, and he had some answer which I don't remember. So there, some properties were behaved nicely, as it happens with prime manifolds and their connected sums. Connected sums are not exist, but they may not be unique. How you join may not be unique, but they exist. So something must happen with some of these properties when you take connected sums. What is it? And why are there so many different ways of saying the same thing? Completely different.
That's a good question. Yeah. So connected sums. So like for Khovanov homology, connected sums, there is like a formula for computing connected sums. I am not the person to talk to about what Witten says about Khovanov homology. I have tried to read that paper, and not. Yeah, I would defer to the physicists in the room to understand sort of that approach. But like on a purely algebraic side, we can write down what happens under connected sums of knots and links in Khovanov homology. It's not all that hard. I mean, the state sum decomposition of Khovanov homology, you can pretty much write down exactly what the chain complexes look like, and it's really not bad from a sort of purely Khovanov side. The physical interpretation, that I don't really understand the physics enough to comment on that, unfortunately. So.
Okay. Go ahead.
I was just probably connected to the previous question, what you mentioned is the quantum computing. Well, actually, you mentioned the limits of the classical computing approach. And I was wondering, is there any problems in the theory where a false quantum computer would be, if there was one?
I don't know of ones off the top of my head. Yeah, like a Shor's algorithm type, I don't know of any. But that's not to say that I certainly haven't thought about the quantum set at all. So I know that there are people who think, like low-dimensional topologists, who think a lot about quantum, and okay, actually, if you talk to me after, I might be able to point. There are people who have thought about it, but I don't have any. I don't know enough about what problems. They're not. At least the overlap of the problems that I think people have applied ML to, and the overlap of the problems that people have applied quantum computing to, there's not really any overlap there. But there are certainly people who have thought about quantum computing and low-dimensional topology, and I think have probably come up with things in that realm, but they're sort of pretty disjoint from the problems that ML people have sort of tried. So.
I what was I going to say? I think you kind of addressed it already. Just going back to when you were talking about using the machine learning for like predictive models in mathematics, and you did mention all right, like maybe mathematicians aren't happy maybe to accept it quite yet. But I was wondering because like you get an answer without the solution. That's not what Hughes really. But I was just wondering, is there any way to kind of reverse engineer the models that you train? Like obviously, if it's making predictions and seeing patterns within whatever data you're feeding it, and I know it's a bit of a weird one to quote, but I remember watching a 3 Blue 1 Brown video where he was talking about like computer vision, and like it saw patterns within the images you put in, but sometimes those patterns were nonsense.
Yeah.
Maybe I'm not the right person to say they're nonsense. Maybe they're not nonsense. But is there any way to like reverse engineer the models so that you can actually find new patterns within these knots or whatever area of mathematics you're looking at?
Yeah, so that's a really good question. So this gets into this realm of explanatory machine learning, where we, like if you think of sort of neural networks as giving you these decisions or these predictions that are just completely cloaked in secrecy, you're trying to sort of peek, behind the curtain and see what's really going on. And so this is something that people have used. So Vishnu Jajala, Arjun Kar, Jessica Craven, and they had one other collaborator on this paper where they used explanatory machine learning. I think they were the first ones to use this, and I apologize for forgetting their fourth collaborator, but they used explanatory machine learning to like come up with like sort of an ansatz to like predict the volume using like evaluations of the Jones polynomial. So essentially you train a neural network, and then there's this way to sort of like assign weights to each of the sort of the inputs that are sort of based on what the output values are. And sort of the more that changes in an input value affects the predicted output, that's sort of the more sensitive your neural network is to that input. And then from that, you can kind of try and recreate things. And so they came up with a formula for predicting the volume based on evaluation of the Jones polynomial, which was quite nice. Then there's also this paper that came out in Nature 2 years ago, where essentially some mathematicians, Mark Lackenby, Andras Juhas, and then I know Jordy Williamson. I think there was maybe a few other people with this team at DMind. They essentially took a bunch of knot info and they essentially predicted one type of invariant using some other input invariants. And then they used gradient saliency analysis, which is essentially what I was describing there, to sort of try and tease out relationships between the invariants. And then they came up with this conjectured formula for some invariants, which they then went ahead and proved. So they were able to sort of use the AI or use the ML to sort of guide a conjecture, which they then proved using paper and pencil. There's also a really kind of cool project going on, which I'm not involved with at all, where people are using like these automated theorem provers and essentially taking large libraries of formalized proofs that people have written in these automated theorem libraries like Lean, and essentially they are training machine learning models which can sort of like, given a statement that you want to prove using this like automated theorem prover, what it does is it sort of pulls up all the possible sort of like steps you could use. So say you're trying to prove that the GCD of n and n is equal to n, then it sort of pulls out all possible next steps you might use in your proof, and then it somehow picks the best one, and then you apply that step, and then you repeat the process. So there are people that are like basically trying to apply RL or these sort of ideas to like formalized theorem libraries. And so I think that they have been able to like, they have this Lean dojo, which I have here. They were able to sort of prove 65 new theorems in this formalized mathematical theorem proving language. Now these were not like 65 research level theorems, but rather 65 theorems mathematical statements that didn't show up in the training set, that weren't in the library. They were able to prove new ones using this. So we're still sort of a long ways away from, I think, being able to like formalize research level problems, and maybe that day will never come. I don't know, some people think it's sooner than later. But we do sort of see definite exciting steps in that direction where people are formally proving theorems using ML. So
when you're studying these like expanding neural networks or like your neural networks, is the structure generally like a perceptron? You're studying the weights on this, or
yeah,
have there been any other structures that have used or stuck to the standard approach?
like as opposed to like a feed-forward neural network, or
like a convolution or something?
yeah. So people have used like graph neural nets. Like knots have like a natural graph structure, so people have used like graph neural nets. I know people have like used convolutional nets to like take like say a diagram of the knot and then try and classify using a convolutional net. So like definitely other architectures, neural network architectures have been used. The ones that I mostly like, the stuff that I was talking about early on was all just straightforward feed-forward networks, like transformers. I've got a project with some transformers that we're trying to use. So I think a lot of stuff that comes out of the ML side of things finds, you know, people have tried or are trying, or like there's definitely interesting things you could try using different architectures.
Is there any reason you went with the structure that you went with? There was
the first one that I talked about, because I didn't know anything about neural networks at the time. So honestly, in 2016, so this was like this I think was like the first knot theory paper that, and it was essentially like I was finishing up a visiting position. I'm like, oh, I might need to get a job in or I might need to like get a job in industry somewhere. So I should learn some neural networks. And I was like, well, what's an interesting data set? And knots were like, I was a knot theorist, so I was like, well, I should try some knots. And so really, it was kind of the first thing that I think anyone had tried at the time. And so there's no reason I think to try anything fancier than just a feed-forward vanilla, you know. But since then, like I've been more interested in like more complicated architectures, and I think depending on the problem you're trying to solve, there often is a good reason to go with something more complicated than a feed-forward neural network. So.
Can I ask a question?
Oh, yes.
Thanks. I'm curious about this example that you had at the beginning of what you called, I think, E8 manifold.
Oh, yeah.
And I was wondering, this is made of, your diagram was made of rings, which are arranged as the E8 linking diagram. Is this something that you can do for all linking diagrams of simple algebras?
Oh, can you represent?
If I take any other linking diagram, but let's take to begin with the simply laced ones, and build a set of rings arranged as that linking diagram. Do I get something meaningful?
Yeah, you can certainly take any Dinkin diagram and interpret it as a Kirby diagram. I don't know off the top of my head, like there's this, if you draw a random link with numbers attached to each component, you can certainly build up a four manifold with boundary using that information. But it's not, you're not always going to get, you have to sort of, the manifold you end up with has to have sort of a boundary of a certain form in order to guarantee that it can be closed off to get a closed four manifold. And so if you pick like a different Dinkin diagram, you can certainly build like a manifold with boundary using that diagram. It's not obvious to me whether you would get something that can be closed to get a smooth closed four manifold though.
And for the non-simply laced ones, presumably you need to use something other than rings or cross them in different ways.
Sorry, I'm sorry, could you say that again?
But in the case of the non-simply laced ones, where you have roots at different angles, and so different links in the Dinkin diagram, you would need something more complicated than just rings, presumably, or cross them in some. But in other words, you cannot just put -2 on each of these rings, presumably.
Yeah, the fact that those are -2s is not necessarily like it affects the diagram you end up with, but you could put any sequence of integers there and end up with a perfectly good prescription for a four manifold with boundary. And you could delete as many components as you want, or add in, I could replace any one of these components with a trefoil or any non-trivial knot. And again, the way in which you build a four manifold still works, but it just changes the four manifold you get.
So that's actually the next thing that I was going to ask. I was wondering what happens if you add an extra ring on the right-hand side of your picture. That would be the E9 diagram, which as an algebra is infinite dimensional, but in terms of your construction, it still yields a four-dimensional man.
Yes, it would still give a four manifold with boundary. Now, whether or not that could be capped off to give a closed smooth four manifold, I'm not sure. I'd have to play with the diagram a little bit and see if you get essentially you need the resulting boundary of the four manifold to be a boundary sum of S2 cross S1s. So there's like some particular form that the boundary has to be in order to get a closed four manifold. But you could add components, you could change the framings, you could change any of the components to non-trivial knots, you could change the way that they link, and that still would give a smooth four manifold with boundary for sure, and possibly a closed four manifold, though it's harder to tell if it's closed.
Can I ask?
Thank you.
Oh yeah. Did that answer your question?
Yes, thanks.
Okay.
There should be some cobordism theorems on this, no? Isn't it? For example, I know that four manifolds with Lorentz, there is no Lorentzian cobordism between three manifolds.
Yeah, so like four manifolds are classified up to cobordism by their signature. So there's the signature of the form, the intersection form, is uniquely classifies when two four manifolds are cobordant. So if they have the same signature, they're cobordant. If not, they are not cobordant.
But when you cap them, you're starting from nothing and going to this as a capping surface, right? So there's a cobordism theory coming there.
Yeah. So so I guess you're talking about one dimension lower. Yeah. So you're talking about like three manifolds. So every three manifold. Every closed three manifold is the boundary of a four manifold, and that's kind of implicit in some of these constructions. Like the fact that you can get any closed three manifold using Dane surgery is essentially like if you know that every three manifold is closed three manifold is obtained using Dane surgery, you can show then that every three manifold bounds a four manifold by just doing the same Dane surgery, but interpreting it as a Hamilton decomposition. Yeah, I don't know if that was what you were getting at.
We can move.
Yeah, we can thank Mark again for indulging us.
Oh,
That's fantastic.
Thank you.
We learned a lot.
Good.
I learned a lot.
Okay, I'm glad. Thank you for your questions and participation.